High-speed imaging is ubiquitous throughout modern science. For example, it is used in biomechanics to capture the fine micromotions of animal movement, in fluid dynamics to measure the fast flow of liquids and gases, and in many other science and engineering disciplines. However, existing high-speed cameras have several practical limitations. For example, off-the-shelf versions of such devices are typically very expensive, costing tens or even hundreds of thousands of dollars. More importantly, they have very high bandwidth requirements. In practice, that means that these devices can only record high-speed video for very short durations without having to reduce resolution, limiting their practicality. To address these issues, on the research side, a number of techniques have been proposed that aim to optically compress the high-speed signal during capture. In one line of work termed coded exposure, the sensitivity of individual pixels is modulated over time during the camera exposure. While such approaches have demonstrated impressive results, they still rely on experimental sensors, making them hard to implement in practice, and such available sensors are often slow, limited to just a few thousand FPS. They also struggle with sparse scenes, an important class of scenes that are present in many real-world applications of high-speed video. To tackle these challenges, recent work has proposed a new methodology with two key components. First, spatial multiplexing optics are used to spread the light from a single point over a larger area called the point spread function. Second, a single row of this point spread function is then captured for each time step. Because a single row can be captured extremely quickly, a high-speed video can then be extracted with an appropriate reconstruction. These setups are simple, requiring just a few pieces of off-the-shelf hardware, and they are also quite fast, with capture previously demonstrated at about 100 kHz. However, these setups can only handle spatially sparse scenes thanks to only a single row being captured for every timestamp. They are furthermore very light and efficient for the same reason, limiting their application for even faster scenes. Our work attempts to address these aforementioned limitations. Our proposed device is again simple to construct with hobbyist equipment and also extremely fast, allowing for capture at up to 196 kHz. However, improving upon past work, our system can handle a more general class of spatiotemporally sparse scenes, expanding real-world applicability, and it is also extremely light efficient, making it much more robust to noise. Our device is based on changing the point spread function of our camera over time to encode temporal information. To implement this, during the camera exposure, we simply rotate a diffraction grating in front of the camera. This diffraction grating leaves a unique rainbow streak on the sensor for each timestamp. By identifying which rainbow streaks are present in the final captured image, we can potentially disambiguate the high-speed motion. In short, we can take this frame and plug it into a standard deconvolution algorithm and reconstruct the original high-speed video. In our work, the entire sensor is always exposed, while only a single row is exposed in past work. This results in powerful benefits for our methodology. For one, this results in improved robustness to noise, as more light from a point is captured by our sensor. Our system can also handle a wider class of sparse scenes, namely, our camera can reconstruct spatially dense but temporally sparse scenes that past approaches struggle with. We describe these aspects in more detail in our paper. Let's see some real-world results. For the results we show here, our camera is set to capture at 45 FPS, but our encoding reconstructs a high-speed video at over 6500 FPS. We show an example of our system capturing it at 196 kHz in our paper. Like past work in spatial multiplexing optics, our system can reconstruct generic spatially sparse scenes with extremely fast-moving bright objects. Our system can be applied to real-world applications like motion capture in order to image high-speed human motion, or particle image velocimetry to track fast fluid flow. Our system can also capture high-speed video of spatially dense but temporally sparse scenes. Here, a spinning fan is strobed twice by a light at unknown times. Our system is able to resolve the two strobes. In summary, we propose a low-cost high-speed camera based on rotating the camera optics during the camera exposure. Compared to past work, this novel formulation results in improved robustness to noise and applicability to a wider class of spatiotemporally sparse scenes. Thanks for listening, and please see our project page for more details.